Here are solutions to homework set number 7 for ECE 376. This homework set looks at data collection and using a student t-distribution. Now, the first problem is to collect data. So what I'm going to do is set up an experiment where I measure the capacitance of a capacitor. So there's a 100K resistor on your PIC board. This is a 100 microfarad capacitor. So I'm going to first charge it up to 5 volts, and that shows up here. The logger program measures the analog input, converts to voltage, and displays it on the LCD, and sends it to the serial port. When I take off the 5 volts, I can watch the capacitor discharge. Record that data. That should be an exponential decay as e to the minus t over RC. So once I collect the data, throw that in MATLAB and repeat 3 times. Same capacitor, same polarity, same measurement. If I do that, I should get the same answer, and I don't. It's really close. Again, it's the same capacitor, but it's a little bit different. So in that case, these are my 3 voltages versus time. What I now want to do is find the time constant. So this is decaying as your V0 e to the minus t over RC. And t over RC is a constant, so that's going to be your V0 e to the minus bt. To find b, I'm going to plot the log of voltage versus time. So this is your voltage versus time. Take the log of voltage. That's the log of V0 minus bt. So the slope is what I'm looking for. Take the log of voltage, plot the log of voltage versus time, and the slope is what I'm trying to find. So to do that, I'll do a least squares curve fit. My basis is just time and 1. Then using least squares, it's the inverse of B transpose B, B transpose times Y. And Y in this case is the log of voltage. Do that for my first data set, second, third data set. And that's the number that I want. That's my slope. Pull up those 3 numbers. That's my 3 measurements of the same capacitor, same polarity, same time of day, same temperature, something like that. Just due to, experimental errors, whatever. You're always going to get different answers. They're close, but a little bit different. And just for fun, I'm going to convert to capacitance. My sampling rate is supposed to be 10 milliseconds, or 100 milliseconds. Actually, 10 milliseconds. So 1 over RC is my slope. I know R is 100K. Solve for C. So if I do that, then the capacitance in microfarads is just 10 over this number. So the capacitance that I measured was 44.11, 43.54, 43.29 microfarads. For the homework set, you can use either data set or either number. I'm going to use microfarads because that's kind of meaningful. It's supposed to be 100 microfarads. What that tells me is that either the capacitor is really mislabeled, or R isn't 100K, or my sampling rate's not really 10 milliseconds. It's probably this case. My code takes some time to send the serial data, takes some time for the A to D, takes some time for the waiting. My timing's a little bit off. When we get to interrupts, I can make this more precise and get better measurements. But for now, this is what I got. So taking my data, problem 2 is, that's problem 2. Problem 3 is now find a 90% confidence interval. So I've got 3 data points. It's got a mean, has a standard deviation. From StatTrack or t-table, if I have a sample size of 3, meaning 2 degrees of freedom, if I want 5% tails, again, here's what your distribution looks like. I want this tail to be 5%. I want this tail to be 5%, leaving 90% in the middle. 5% tails corresponds to a t-score of 2.92. So I'm going to go left and right of the mean by 2.92 standard deviations. And that gives me 44.89, 42.41. So that's my 90% confidence interval for the capacitance, based upon my measurement. Yeah, measurement's kind of iffy, but given that measurement, that's my confidence interval. Basically, my capacitor meter needs to be calibrated, or I need to get a more accurate measurement of time. That was the first set. Now, do something different. What I did is I took out that capacitor, put in a different one. So it's also 100 microfarad capacitor from the same bin from Jeff, but using a different capacitor. Now what do I get? Due to manufacturing tolerances, there will be a difference in the capacitance. Collect the data one more time, pull out the data. I started at 100 because typically the data was flat, then start rolling off. So I'm going to throw out this part of the data, first 100 data points, stop at 900, just so they're all the same length. It's not necessary, but it makes my plotting easier. Then plot the data. Second capacitor, here's the voltage versus time. Repeat the last procedure to find the capacitance, do a least squares curve fit for time, 1, and log voltage. I get my parameter, that's 1 over RC. That's my 1 over RC time constant, solving for C. For the second capacitor, that's its reading. And given 3 readings, I can use statistics to find the mean, standard deviation, 90% confidence interval. So based upon my data, I'm 90% certain that this capacitor is in the range of 41.53 to 42.05 microfarads. Finally, comparison of means. What's the probability that A is bigger than B? So here's my data points, the 3 data points for B, second capacitor, 3 data points for A. There's kind of 2 ways to analyze this. One is for an individual, one's for population. An individual would say, if I take one more measurement, what's the probability that the measurement of A will be higher than the measurement of B? And there is a chance I could get a high measurement for B, get a low measurement for A. That's for an individual. To do that, I create a new variable W that's the difference between A and B. The W's got a mean, the difference in the mean, and the variance is the sum of the 2 variances, variance of A plus the variance of B. Take the square root, I get the standard deviation of W. And the standard deviation is going to be bigger because, again, I could get a low B, high A. So the standard deviation is the spread. The spread gets bigger. So this adds, it doesn't subtract. What I'm left with then is a new distribution for W. It's got a mean of 1.86. Here's 0. And what I want to do is find out how far is 0 from the mean in terms of standard deviations. So this area over here is A is greater than B. This area over here is A is less than B. To find out the area that A is bigger than B, find the distance to 0. The t-score is just what's the mean of W divided by the standard deviation of W. That's my t-score. It's 4 standard deviations away. Going to StatTrack, I've got sample size of 3, meaning 2 degrees of freedom. T-score of 4.3 with 2 degrees of freedom is 97% chance. So 97% chance my next measurement of A will be higher than the next measurement of B. A second way to analyze this is the population. Capacitor A does have some value. I don't know what it is, but there is some value. As my sample size increases, I get a better and better idea what the value is. So I need to take sample size into account. For populations, you divide the variance by the sample size. So I get a new variance of W, a new standard deviation for W. Find the new t-score. I'm 7.54 deviations away. So in terms of the true value of A versus true value of B, now the W distribution looks like this. The mean is 1.86. That didn't change. But because my sample size, I am now 7.54 deviations away from 0. Converting that to a probability using StatTrack, that probability is 0.991, so 99.1% chance. Of these 2 capacitors, there's a 99.1% chance that A actually is larger than B. Now this is where the term significant has different meaning than English. This is statistically significant, saying I can tell the difference between A and B. In terms of, is it practically significant? Do I care about the difference between 43.5 and 41.6 microfarads? Probably not. So it's not significant from a design standpoint, but it is significant from a statistical standpoint. I can see that difference. And if I have enough data points, the standard deviation drops as the square root of n. As my sample size goes to infinity, I can see very, very minute differences. Again, that's where it's significant from a statistical standpoint, may not be significant from a practical standpoint. So that's homework set number 7 for ECE 376.